Hello everyone, welcome to my talk. I will talk on quantum computing, and the first weird thing that I'm going to say, and there will be many, is that when you flip a coin without looking at it twice, and then you look at it, it will always end up in the original state. So, to start, who of you knows Schrödinger's cat?
I'm not sure.
Alright, who thinks it's alive? Alright, and who thinks it's dead? Alright, so you say that it's neither. I'm saying that, is it alive? Well, yes, but actually no. And what? Oh, there's a really enormous delay. I'll have to plan on that. Alright, so to explain this weird behavior, we first have to ask the question: what can computers do? What do we like them for? And I think that it is because there is really precisely given what is yes, what is no, and that will be either 1 or 0. But in a quantum world, there is a maybe, which we don't really know how to represent. And in a quantum computer, it's most of the time, which could be quite annoying. And if you didn't know what to do, except for, it's not really a maybe, it's more of a yes, no. There is no maybe in a quantum world. Most of the things on the quantum scale don't really like to have one state, and they don't really like to occupy one place at one time, and they really like to do everything at once and decide what they are doing once you look at them. So a great example of this is Schrödinger's cat, where originally it was an argument against the theory of the quantum theory, where Heisenberg said, wait, if it works like this, then if I attach some quantum state to a mechanism that is attached to a hammer, it would break a poison, and I place it with a cat in a box, and I have a 50% chance of the quantum state activating the mechanism. There is a moment where the cat is dead and alive at the same time. I mean, that is absurd, right? How can something be dead and alive at the same time? It is either one or the other thing. It doesn't decide when I look at that. Why would it behave like that? And again, yes, it is absurd, but actually no. And that's why we will have a look at some maths, because everybody likes maths, right? Yay! And there is this company called Q Latvia, and they are doing trips around Europe, and we will have a look at vectors, matrices, dot products, tensor products, which are all of the really nasty words you should never say unless you are in a very specific surroundings. And I hope I'm in such a surrounding. All right, so. So, they have prepared quite interesting materials where they use a Python notebook for giving examples using a library called QuizKit. And this library allows you to simulate quantum computers, or more specifically quantum circuits, because we aren't really in the part of actually having a quantum computer. We only have some circuits that, which can do this and that, but nothing really useful. I think that IBM did experimental factorization of 15, which is a really huge breakthrough because no other quantum computer did that before. But, I mean, we factorize even large number with classical computers. So, I suppose that everybody already here knows variables, loops, conditionals, and lists. Who doesn't? Awesome. So, we will continue, and now, let's not suppose that everybody knows vectors, dot products, matrices, and tensor products. We have already gone through what a vector is. We have already gone through what the matrix is. So let's see what a dot product is. And dot product would be a result of multiplication of two vectors, and alright, this is a return with the line. There are some. Co?
Můžeš to otočit dát znovu na projektor a dívat se na to.
Jo, that's fakt. Okay. So, what a dot product is? It's also called scalar product sometimes. And you can really multiply two vectors in different ways. For example, both in a column, and that's when you would get a dot product, which is basically, wait, which way was it? Yeah. You multiply the first two and the second two and add them to the result. Then the third two you multiply together and add them to the result, and so on and so on and so on. And you can do this with however long vectors you want, but they have to be the same length. So that is what a dot product is. It usually, but not always, makes well, it should make it smaller, but it doesn't really necessarily make the product smaller than the original inputs, because if you, for example, multiply a row with a column, you're going to get, for example, let's say I get 5 columns with 5 rows, I multiply them together, and I receive a 5 by 5 matrix. And wait, we know what matrices are, and what are tensor products. Tensor products make the matrices larger, because when you multiply these, you don't add them. You just put them there to the place where they were. So if I tensor this with this, I get basically this coordinate with, times these 3 separately, so those would be these 3, and then the second coordinate with these 3, which would be these 3. And that would be a tensor product, and you can get very large matrices if you have complicated problems, for example like these, and that is not a thing a human should solve. And once you get to really complicated problems, for example simulating some chemical chains, you can get to really absurdly large matrices which not even classical computer can handle. For example, classical computer can handle, I think, to about 5 qubits if it's average laptop, and afterwards it's basically undoable. So, now let's see, there's also some delay in this. Oh, yeah, I should move it here. Sorry for the complications. start oh, I bet VLC is working. Slideshow. Wait a moment. This. Ah, God damn it. Sorry, I shut down my notebook. I'll have it up and running soon, hopefully. Maybe we should. Alright, let's go through the notebook just now. We can't. We can't go to the presentation, can we? Let's have a 5-minute break. I'll resolve it in the meantime. Right, so we're back from the break after some technical issues. And now that we have gone through some of the maths that we need in order to understand most of the things, there is this thing, coin flipping. We use a coin flip when we want to get something random, and sometimes it even falls, which is even more random. And usually when you flip a coin, it doesn't matter how many times you flip it, and you always get a 50% chance of getting one or the other result. Sometimes it's not exactly 50%, but in a quantum world, when you flip something twice without measuring the result, you always end at the beginning. And alright, so what is happening? What's happening is that there are some really buzzwordy things like superposition, entanglement, and spooky interaction. Spooky interaction is something we use for quantum teleportation, which is not what you think it is. But we can get to probabilistic systems. I think that everybody understands that what a probabilistic system is. Is there anyone who doesn't know what a probabilistic system is? Awesome.
A bit.
Sorry?
Maybe a bit.
Alright, so let's explain that. When I flip a coin, I have a probabilistic system because I might get tails, I might get heads. And it should be 50-50. You can have biased coin, and there are some random operators you can use, for example. And this is quite a counterintuitive table which they use in quantum mechanics, but it should be quite easy. For example, here is a classical identity, but what one wouldn't expect is how this is structured. And it's structured in such a way that the original state is over here, the result is over here. So for example, if I apply not, I get a 0 from a 0. If I don't apply the knot, I end up with the same result. If I apply the knot to a 0, I get a 1. If I apply a knot to a 1, I get a 0. And if I don't apply a knot to a 1, I get a 1. Same goes here. If I apply a 0 operation, I get a 0. If I don't apply 0 operation, I get a 1. And so, and vice versa for one operation. So, this is how the operators work in quantum mechanics. And now that we know how to write it down, let's get to some basics of quantum systems, which are very similar to the probabilistic ones, but there are some extras which are sometimes very hard to comprehend. And let's take a look at quantum coin flipping, which I was trying to explain at the last lightning talk, and I didn't have enough time to do that. And now that we know what matrices are, and what probabilistic systems are, etc., I hope it will be easier to comprehend. Alright, so let's say that we have a photon source, because a photon has quantum attributes. Or, yes. And for example, it could be a polarization. And when you have a polarized photon, it might pass through something, it might not, depending on how it's polarized. And let's say that it can be 1 or 0 based on the orientation. So, when we have a beam splitter, for example, based on the polarization, it may end up in one of these two detectors. And as you would probably suspect, this ends up being 50-50. Because if you shoot many random photons, you get these. If you shoot many photons, there's a 50% chance that it either passes through or gets reflected. When it passes through, we call it that it's in state 0. When it gets reflected, we call it in state 1. Now, when we have this system, we can try to measure whether it gets reflected at the first mirror. And now it's 50-50. It might get reflected, it might not. If it got reflected, it's caught by this sensor. If it did not get reflected and passed through, it gets reflected by a mirror, which always reflects. And then we are flipping the coin again. And what do you think are the probabilities of it ending in A, B1, and B2? Who thinks it's 50% and then 25 and 25? I think it is like that, and the two of us who raised the hands are correct in this particular example. But now there is this example. There is no detector here, so both state 1 and state 0 get combined here, and then we try to measure if they land in B1 or B2 sensors. So, one might think, alright, it doesn't really matter when I flip the coin, because we have clearly seen that state 0 always gets, state 0 always has 25% chance state 1 should 2, which it does. But something really weird happens. One might suspect it again will be 50-50. But if we skip some really boring maths, we will find out that it ends up being 100% and 0%, because we flipped the coin twice without looking at it in the meantime. And this is basically what happens in the quantum world, and we can explain this by a Hadamard operator, which is named after the scientist who brought it up, obviously. And is there a matrix somewhere, or is it later on? Right, this is just how it works. We've already explained that. And yes, so this is how do you represent a qubit. It's a vector which has two coordinates, so this is a real valued qubit. There are also imaginary qubits, which we won't dive into because that would be too many numbers. And for example, if we want to switch the qubit with matrix, use this one, and this is the NOT operator. So if you paid attention to the first talk, you should know how it does it. And this is the Hadamard operator. It basically flips it according to one axis, which is located at square root of pi, and that would be, if I skip to visualizing, here, drawing qubit, there should be. So this is how we would visualize a real valued qubit, where if we have 0, it points points straight the x-axis, and if it's value 1, it's perpendicular, either this way or this way. So in the quantum world, there is a difference between between 0 and a -0. And what Hadamard operator does, it takes this axis and flips it over. So, when you apply it twice without actually measuring the qubit, it takes the axis again and flips it back. So it's at the 0 state again. And now you would think, alright, but when do I measure the qubit at the state where it's in the half, where it's not perpendicular, or when it's, for example, at 45 degrees? You don't. That's the problem of quantum computers, and that's whenever you measure the qubit, you destroy its quantum state and it collapses to either 0 or 1. There is nothing in between once you measure it. And to see some examples, let's see the code on one qubit. There should be some notes somewhere. Oh, these are our exercises. Right, quantum state. So this is basically the these are our exercises. Right. We've gone to quantum states. Let's see superpositions. Alright, so a qubit is in a superposition when it has a probability of being at a specific state. It can be either in 1 or 0, but actually it's at both states, and we will see why later. When you have only one qubit, you don't really know. Well, you know it's at both states at the same time, but you don't know what will it end up when you measure the qubit. And I swear there was a lot of prepared code to try out, but when I'm looking for it, I can't find any. Right. Oh, there it is. Right, so for example, here's a circuit that is basically consisting of some registers. There is a quantum registry and a classical registry. And the classical registry is the thing you have in your normal computer, and it uses bits, and we already know what it works like. And these are the weird ones. And we are interested in those. So, for example, we can flip the registries. Note that they start at 0. But these aren't Hadamard's, these are actually flipping them, like from 1 to 0 to the actual 1 or 0. And they aren't doing anything random. This is basically a knot. And this is a control knot, which is a really interesting thing. Because control knot flips the second bit if the first one is 1. Now imagine that we have 2 qubits, and I apply the Hadamard to the first one. I get it in a superposition, which means it's at both states at once. And now I apply a controlled knot, which means if this one is true, flip the second qubit. What happens? Well, the second qubit is both flipped and not flipped at the same time. And how do you know that it is or is not? It's when you measure one of those 2 bits. So if you measure the first one and you see that it is not 1, then the other one is not 2. And if you measure the second one and you see that it is 1, then the other one is 2, 1. So this means that they are correlated in normal mathematics, that they always will be in the same state because they both start at 0. The first one is set to random and the second one is set to switch when the first one is true. And this thing is called entanglement, which should be described somewhere here. Reflections. 2 qubits, superdense coding, that's it. Should be. Alright, yeah. So, this is basically what I've explained. Here we have a random, a first qubit set to superposition by the Hadamard, which means it's exactly yes and no at the same time, true and false, not just one of them. And this is described as a vector by describing it as half the probability, 0 probability, 0 probability. Now, what does this mean? It means we have 2 bits, that means 4 combination. This is the probability of the first combination, of the second combination, of the third combination, and of the fourth combination. I think that you know where I'm heading. Who's entirely lost? Alright, so the Hadamard operator sets the qubit to a state where, when you measure it, it switches to 1 or 0 at the same probability, right? Now, I've only flipped one of the qubits, which means the second one won't move. So this would be 0, 0, I have half the probability. This would be 1, 0, I have half the probability. And it will never be 0, 1 and 1, 1, because I didn't do anything to the other one. It started at 0, so it will always be 0. Who is still lost? Awesome! Alright, so now we can apply a control knot, which is this also matrix, that when the first one is true, the second one will get flipped. So we have half the probability of both being 0 and half the probability of both being 1. That means if I have a qubit prepared, if I have 2 qubits and I put them in an entangled state, and I send one to you, we have we can be sure that we find them in the same state. And this interaction is what Albert Einstein called spooky interaction, because it is faster than the speed of light. And when you measure one, you can immediately measure the second one with the same result. How much time do I have?
You're the timekeeper.
But not when I'm giving the talk. Alright.
Time is relative.
That's actually in contradiction with this theory.
You both have time and not have time.
Yeah.
Unless to check.
Alright, I want to check. Alright, so we are running at 50, so 10 more minutes. And this is called superspace coding, because now the two qubits share the state, and by putting them in superposition, you tensor them. That means by just using two qubits, you have this huge matrix of real values, which collapse into 2 bits when you measure them. Now, what is this useful for? I have some code prepared. Don't worry, I'll make it larger and switch. Alright. Change profile, present. Awesome. And for example, with the coin flip, do I have seen us somewhere? There's rotation. I don't think I have seen us anywhere. Alright. Let's get back to materials. And the quantum communication. I think I'll skip and give the last example, which is Grover search, which is a quantum algorithm. And this is really complicated maths that when you go through all of these materials you should be able to comprehend. But what I want to say is there is using a specific way of putting things into superposition and entanglement, you can create a system where by measuring a qubit or a set of qubits, you will receive a result which will tell you where some element in a huge list is hidden. And basically, in a real list, when you want to search for something, you need to go through all the elements to get some real chance of finding the element you are looking for. And using this quantum algorithm, you can just mark the element you would be looking for later, again by putting it into a specific quantum state and entangle it with a set of bits called the oracle. It's called the oracle because it always knows where it is. And by just doing a square root of iterations of this algorithm, you have a pretty high chance of actually finding what you are looking for. So the interesting part would be at the bottom, I think, where there is explained that if there is a single marked element in the list of given size, you just need this number of iterations to find what you're looking for. The problem is that you already have the element marked, and you can't really decide, alright, now I want to find this element, but I haven't marked it, so I want to find it instantaneously. That's not the thing where we are yet with quantum computers. but you can play with it around in Python. And I can provide the materials as Q Latvia allowed me to share these materials. They want to open source them. And I think it should be able to pin them to Pyvo websites, right? And so, yeah, should you have any questions, I'll be glad. And I also have one question on you. If there's anyone interested in mathematics, I would really love to try if we could find a way to build basically any matrix using a few qubits by rotating them and putting them into superpositions and basically doing some actual calculation with them. So that would be my talk. Any questions?
We're all overwhelmed. Thank you.